Okay, hello guys. So today we're gonna begin a new chapter. We just finished discussing the notion of limits, continuities, and so on. And now we're gonna continue analyzing functions. And this time we're gonna introduce the idea of derivative. Okay, so the basic question that we want to answer in this question is the following. So given a function, suppose that we have a function. So given a function y equal f of x and a point on its graph. Okay, let's call it P, and the point P on its graph. What we would like to do is we want to make sense of the tangent line of the function at that point. Okay, so given a function and a point, the question is how do we make sense? And by this I mean how do we define, okay, how do we make sense of the notion of tangent line? Okay, at the point P. This is the question that we want to answer. So let's put this in perspective. Let's draw a little picture here. So let's say that we have a function. So this is a function y equal f of x. And let's say that we have a point P over here. And then as you know, the tangent line is the line that touches the graph of the function at P. And you know, it does not. So around P, it only touches the graph at one point, namely P. I say around P because it could be that away from P, then it crosses the graph again. Like for example, if I were to extend this line, right, it's gonna cross the function one more, but this is far away from P, okay? But around P, it only touches the graph at that point. So you know that this has equation y equals mx plus b. You know, the question is, okay, what is this equation? How can we make sense of this line? How can we find the equation of this tangent line? Okay, so this is the question that we want to answer today, but this is a very general question. So let us start with something that we are more comfortable with. In particular, let's talk about the circle. Okay, so for example, let us say that we're looking at a circle, that the curve that we have in the plane, because we're going to see later that it doesn't have to actually be a function, it may just be a curve. Okay, so let's suppose that we have a circle. Let me draw a nice circle here. And the reason why I'm bringing circle is because this is a shape that you have been studying, you know, it's a long time in school. And we have a special definition for a tangent line when it comes to a circle. So let's take advantage of that. So as you know, when we have a circle, there is a center, right? And then the circle also has a radius. Now let's say that we have our point P somewhere in here, and a theorem from geometry actually allows us to define the tangent line to a circle at a point, because actually the tangent line is the only line that touches the circle at P and at the same time is perpendicular to the radius. In other words, when you if we draw the tangent line at P for this circle, let's put it here. A property is that in this case, if we draw the radius of the circle, which as you know is the line segment joining the center and a point on the circle. So if we draw this radius, then a theorem is that this is 90 degrees, and this is the only line that satisfies this property. So tangent line, and this is in the case of a circle. So for a circle, yes, we can make sense of the tangent line. So the tangent line of P is the unique line that touches the circular P and is perpendicular to the radius. Okay, there is only one line, and that's the tangent line to the circle. But of course, here we are using the fact that there is a center, there is the notion of a radius, and all of that. And how do we translate this to a general function like the picture that we have above? So this definition, even though is very nice for circles, it's not that straightforward to translate this definition back to our function. And so we would like to find an alternative way of making sense of this. Okay. All right. So let's do that. So one observation though. So remember, our job is to be able to, given a line, to be able to find the equation. I mean, given a function at a point, we want to be able to find the equation of a tangent line at that point. So in particular, because we want an equation, let us spell out what we need. So what do we need to be able to write this equation? So we need a point, and remember, we also need the slope. So to find the equation of a line, you need a point and you need the slope. Well, the point, remember, we have it. What is the point? Well, let's say that P has coordinates a, comma, f of a. So let's say that, mm, okay, so let's go here and let's say this is f of a, right? So the point P, we have it. The point is a, comma, f of a. So really, what we don't know is the slope, okay? This a, comma, f of a, this is our point P. What we really don't know is the slope. So really, when I say let's make sense of the tangent line, let's define this tangent line, the focus should be on defining the slope of this tangent line. Because the point, we know it, okay? Once you have the slope, then we can find the equation. So the question is, how do we make sense of the slope? Okay, so now that we are directing our focus is on the line, remember the tangent line, but in particular, our focus is the slope now. Because once you have it, we can find the equation because we already have the point. Okay, so how do we make sense of the slope of a tangent line? Let's go back to the picture of the circle. Okay, so we already defined it one way, but another way to make sense of this would be as follows. For example, I could start with a point, and I kind of hinted at this at the beginning of the semester when I was introducing the notion of limit. So let me start, we have the point P. I'm going to start with another point. Let me put it over here. I'm going to call this point Q. And the reason why I'm putting a second point is because, remember, I'm now after a slope. The moment that I have 2 points, I can find the slope of a line that contains those 2 points, okay? So the idea would be, okay, let's draw the line passing through P and Q. Q is another point on the graph, in this case on the circle, okay? And let me, so the slope that I want, which is a tangent line, I'm gonna call it M, okay? Now, let me call this one, the slope of this line is gonna be the slope M, I'm just gonna call it MPQ. Let me call this Q1, okay? So MPQ1. So this is the slope of a secant line. This is called a secant line. Now, of course, this slope is not the same as the slope of a tangent line. Look at the lines, they are different. However, what we're going to do now is we're going to make this point Q, Q1 in this case, we're going to make it closer and closer to P. So let's see. Let me put another one here now. Let me call it Q2. And let's repeat the process. Now, I'm going to draw my secant line passing through P and Q2. Okay. And then we get a second slope, MPQ2, and so on and so forth. So the idea is that now this point is gonna get closer and closer to the point P on the circle, okay? And as we get closer and closer to the point P, we start watching what happens to those secant lines. And then hopefully you see that the closer the point Q is to P, the closer our secant line will be to the tangent line, okay? So the idea here is, the idea, um, we want to make sense of the slope. of the tangent line. So to do this, we look at a point, or let me say another point. We look at another point away from P, and compute the slope of the secant line, uh, PQ. So another point is called Q, which is away from P. Okay, and then compute the slope of the secant line PQ, because now we have 2 points, so we can find this slope, and then we move this point Q closer and closer to P, closer and closer to P, and keep track, and put all of this in quotation marks, so we're going to make sense of this now more formally, and keep track of the different slopes, so of the slopes that we obtain as they will get closer and closer to our slope M, to our slope M. Okay, so in other words, what I'm just saying is that hopefully you realize by me writing all of this that what we're actually doing is a limiting process. Okay, so we are taking a limit. We need to make this more precise now, but it's basically a limit as the point Q approaches the point P, and the limit of what? Well, the limit of the slope of these secant lines. And what we're saying is that in the limit, these slopes of secant lines is going to approach the slope of our tangent line. So what this paragraph here entails is the following, that this slope M that we are after can be obtained by taking the limit as the point Q approaches the point P of the slope of all the secant lines QP, PQ. Okay, putting this in quotation mark because now we need to make all of this precise. But hopefully, the point that I want to make here is that if you want to be able to define this slope M, then we are going to be considering a limit. Okay, now to understand this, we need to be able to say what do we mean by the point Q approaching P. How do we write this in a nice way mathematically? And also, we need to come up with an expression that keeps track of all the different slopes that these secant lines are going to have. And then the limit of this is going to be how we're going to define the slope of our tangent line. Now, if we come back to our picture, okay, let me just keep that picture there and draw a new one. So, will this idea work for a general function? And notice that here we actually didn't use anything special about. So let's put our function here. Let's say that we have a general function y equal f of x, and then let's say that here is, let me put it over here, here is a point P, and then once again the idea is here will be our point Q. We look at the secant line through P and Q. So this is, so this line, the slope is MPQ, and then as the point Q approaches the point P, hopefully you can see that indeed the closer Q is to P, the closer the secant line will be to the tangent line in question. Okay, this one has slope m. So, the same idea that we're using for the circle now applies to any function. So this is a good point. This is a good starting point to make sense of the definition. So, how do we make Q get close to P? That's not too bad to say. The question is, and you're gonna see that in a second. In fact, let me show you that in a moment. So remember, let's say that P has coordinates a comma f of a. So P is the point a comma f of a. Now what we can do is, there is a way, I'm going to show you later an alternative way, but for now, here is what we can do. Let's say here is the point Q, is over here. Okay, so this time I'm doing it from the left, but the same thing could have been done from the right, okay? But let's say that this point, this distance right here, right, is H. And then the point that Q is at, let's call it X, okay? Let's call it X. So I guess in this case, our X would be A minus H, right? So you just subtract H from it. And then if Q was on the right, then that would mean, when I say from the right is because we're approaching Q now. When you look at the graph, it's from above, it's from below the point P, but you could have a Q up here, the green one that I'm drawing, and then approach this way and, play the same game. So in that situation, the point corresponding to it, again, if we call this distance h, would be a plus h. The reason why I'm saying this is because we typically like to think about it this way, okay? Now, if h is positive or negative, so we're going to look at the expression a plus h. If h is positive, that means we're approaching a from the right, so it's the green picture. If h is negative, then we're approaching a from the left. It will be like the black picture corresponding to the red point Q, okay? All right, so the point is that, it's pretty easy to talk about Q. Basically, we look at the X value of the point Q is a distance H from A. And how do we say that Q gets close to P? Well, that's the same thing as saying that H approaches zero. So let me say that Q approaches P is equivalent to require that H approaches zero. So again, if H approaches zero from the right, we have the green situation. If H approaches zero from the left, then we have the red situation, okay? When Q is below the point. But regardless, when H approaches zero, we are doing it from both sides, okay? So that means that in our limit, let's start constructing the limit. Instead of saying that Q approaches P, we can just say the limit as H approaches zero, but we still need to make sense of this piece here, okay? So how do we talk about the slope of the line PQ? And then, of course, instead of P and Q now, we want to have terms that include H, because after all, this limit will be as H approaches zero. Okay, so when we look at this, the question is, how do we talk about the slope of the line PQ? Well, remember that in college algebra, you studied the notion of the average rate of change of a function. And we also talk about this at the beginning of the semester when we talk about velocity. We did some questions about average velocity. And remember, the average rate of change of a function from one point to another is nothing more than the slope of the secant line that passes through these 2 points on the graph of the function, which is exactly the line PQ that we're looking at, okay? So to define MPQ, just remember, or to make sense of MPQ, just recall that this is the average rate of change of f from the point from A to the point A plus H. because remember, the A stands for P and A plus H stands for the point Q. Once again, I'm putting A plus H because if H is positive or negative, it will tell you whether we are in the green or in the red situation, okay? But in general, let's just put A plus H. But basically, this is from P to Q, so that's what the slope of that secant line is. So remember that P is a point, right? And it has coordinates A comma F of A, and Q is also a point. And what are the coordinates of Q? Again, I'm gonna be looking at the green one, but whether H is positive or negative, it will be the green or the red situation. I stress this. But anyways, the coordinates of Q are gonna be A plus H, that's the X value, right? And then F of A plus H. In other words, the slope of the secant line PQ is given by, remember, y2 minus y1 over x2 minus x1. So difference of the y's, so f of a plus h minus f of a over a plus h minus a. As you can see here, the a's cancel out, and so we end up with this expression. And this expression should look familiar to you, okay? If I now, in this expression, if I replace a by x, this is nothing more than what we call the difference quotient, okay? And remember, the difference quotient was a function whose job was to keep track of all possible slopes of the slope of all possible secant lines that you can have on the graph of the function. So this right here, made a note, this is just the difference quotient of f, difference quotient of f evaluated at x equal a. So remember, the difference quotient is, so difference quotient, this was the expression f of x plus h minus f of x over h. Okay? The reason why you study this back in college algebra is because we need it now to make sense of this notion. So you take this expression, difference quotient, evaluated at x equal a, and basically what it does is it's going to give you the slope of the secant line between the point P and the point Q, where Q is this point whose x value has a distance h from A. Okay? Well, the point is that now we have, an expression that we can now put in here to complete our definition. So, moral of the story. So, we can then write that m will be the limit as h approaches 0 of f of a plus h minus f of a over h. Okay? And indeed, this is what we use as our definition. And then, of course, if this limit exists, then we know that we have a tangent line. If this limit doesn't exist, then we don't have a tangent line. Okay? So let me go ahead and define this. So definition, this is the definition of tangent line at a point which we also call it another name. We also call it derivative of f at a point. Okay. All right. So suppose that we have a function, right? So let f be a function. Let f be a function defined on an open interval containing a, so containing the x value a, then if the limit, and the limit in question is, I'm going to call it m, and this would be limit as h approaches 0 of f of a plus h minus f of a over h. So if this limit exists, in other words, if this equals a number, okay, then the line passing through the point a comma f of a, these are point P from our examples, okay, and with slope m, is the tangent line. Is the tangent line to the graph of f, or to f. Let me say to the graph of f at the point a comma f of a. Okay, so that's how we define the tangent line. So sometimes we will also say just at x equal a. Okay, so instead of saying the point a comma f of a, we can just say the tangent line to the graph of f at x equal a. Now this number m has different names. We call it the slope of the graph of f at the point x equal a. We also call it the derivative of f at the point x equal a. And another name is the instantaneous rate of change of f at x equal a. Because remember, it comes by looking at the average rate of change, and then we're taking the limit. So we're making this an instantaneous situation because it's just at a. Instead of just being 2 points, now we only have 1 point in question. When you look at it from the perspective of velocity, if f happens to be a position function, then what we're computing here is the instantaneous velocity, okay? Because the velocity, the average velocity, is the rate of change of the position function between 2 points, between a time interval. But now, if you want to know the velocity at a given point in time, what you need to do is take the limit. So that's just the instantaneous rate of change of the position function. So the derivative of the position will give you the velocity. You will have a homework problem that will deal with this. Okay, so let me write these things down about the different names. So the number m is called the slope of f at x equal a. Also, it is called the derivative of f. Let me stress this. This is typically the way we're going to call it, but sometimes in problems you're going to see, the word slope and so on. So the derivative of f at the point x equal a. Yet another name is instantaneous rate of change of f at x equal a. Okay, all of those are synonyms. The slope of the function, the slope of f at x equal a, derivative of f at x equal a, or instantaneous rate of change of f at x equal a. Notice that I'm always specifying at x equal a because this depends on the point. Okay, so this is very important. So let's see. Let's do an example so we can see this in question. So example, find the equation of the tangent line find the equation of the tangent line to the function f of x equals x squared plus 1 at the point 1 comma 2. Okay, so let's draw a little picture so you can see what we're doing. So basically, x squared plus 1 is a parabola shifted up 1 unit. So this is the graph of our function, right? And then when x is equal to 1, then y is equal to 2. So we have something like this. This is y equal f of x. Here is the point equation, and then our job is to find the equation of this tangent line. This is what we want. Okay, so we want to come up with this equation, mx plus b. Okay, and as you know, we already know the point. So we know the point, we need the slope. So let's see, let's get into the habit of doing this. So what do we need to answer this question? So we need a point and we need the slope. What do we have? Okay, we have the point. The point is 1 comma 2. That's good. The slope, we don't have it. Now, how do we find the slope? Well, we're being told that this line is now whatever line. This is a tangent line. So by telling us that we're looking for the tangent line, we know that to find the slope, we use the definition that we have above. Okay? So to find the slope, as you know, the definition is limit as h approaches 0 of f of, okay, remember, in our case, our a equals 1, right? So this is our a right here. A equals 1. So it will be f of 1 plus h minus f of 1 over h. So remember, it's f of a plus h minus f of a over h. So a is equal to 1 in this case. Okay, so let's compute this. So this is the limit as h approaches 0, f of 1 plus h, we go to the function and plug in. That's 1 plus h squared plus 1, okay? Then minus the value of the function at 1, as you know, f of 1 equals 2 over h. Now, in this limit, notice even if we look at the general definition, if you just plug in, notice that you will get 0 over 0, right? If you take the limit as h approaches 0, f of a plus h will just become f of a, and then f of a minus f of a, you get 0 in the top, and h in the bottom, that gives you 0 as well, so 0 over 0. So that means that every time that you take this limit, you will need to do something, okay? And indeed, if you compute the limit here, you will get, 0 on top and 0 in the bottom. So let's start by, simplifying the top as much as we can, and then we go from there. All right, so I'm going to expand the parentheses. So that's 1 plus 2h plus h squared, and then 1 minus 2, that's negative 1. Then we see the ones cancel out. So remember, our target is to eliminate this h down here. That's the one that's giving us a 0 in the top, in the bottom, that we want to get rid of badly. But now here we see what to do, right? So all we have to do is factor on h in the top, and then we're good to go. So this is the limit as h approaches 0 of h times 2 plus h over h. Now the h cancel out, and when we take the limit, we get 2 as h approaches 0. So we found that the slope m of the tangent line is equal to 2. So now we have everything we need. We have the point, we have the slope. So the equation, I'm going to use the point slope formula. Remember, I introduced this at the beginning when we did the little pre-calculus review. Remember, it says y minus y1 is equal to m times x minus x1. Just plug in your point, your slope in here, and then you can find the equation. So remember, the point is 1, 2. So that would be y minus 2 is going to be equal to whatever the slope is times x minus 1. And now the slope, we know what it is equal to 2. So put it in there as well. Okay. And now just solve for y and write it in the form mx plus b. So y minus 2 equals 2x minus 2. Adding 2 to both sides, we get that y equals 2x. Okay, because the minus 2's, they cancel out. All right, so that's the equation of the line. So we have the y equals 2x. Okay, so remember, so in this case, we would say that this number 2, this is the derivative of f at the point x equal 1, right? Derivative of f at x equal 1 is the number 2. So we write, in these cases, we like to write it like this. We write f prime of 1 equals 2. Okay? So let me actually write that down here. So the number m is called the slope of f at x equal a. Also, it's called the derivative of f at x equal a. We write f prime of a equals m. Okay? And now I'm gonna give you other type of notations that we use, but this is the most common ones that you're gonna see, the prime notation. Okay. Now, before we do more examples, let's go ahead and let us actually do a sanity check, so to speak. So, example number 2. So, find the slope of the function 5x minus 1 at the point x equal 2. Now, why am I saying a sanity check? Because the point is that we know the answer to this question before we even compute. Okay. If you look at the function f, this is the function 5x minus 1. What is this? It's a line, right? And no matter what point you are on the graph, the slope is going to be the same point, there's the same slope, the same number everywhere. That's what it means to be a line. It's a graph that has a constant slope. What's the slope in this case? 5. So there's a 5 right here. So, I call this a sanity check because, when we do our computations, we better get 5 as an answer because that's what makes a line. That's what defines a line. Is this curve that has a constant slope no matter what point you are on the graph. Okay, so let's do it. So in other words, what we're trying to ask here is, now that we introduce the notation, what is this? Okay, so let's compute it. So the slope, this is our m, which is f prime of 2, is going to be the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. So let's compute this. So that's limit as h approaches 0 of 5 times 2 plus h minus 1 minus, so let's see, what's the value of the function at 2? That will be 10 minus 1, that's 9, over h. Okay, so let's simplify this. So this is the limit as h approaches 0 of 10 minus 5h, then negative 1 minus 9, that's negative 10 over h. The 10's cancel out, and then we get, oh, this is a plus here, is 10 plus 5h. Then we get 5h over h, the h cancel, and then this limit is 5, as expected, right? So we are expecting to get an answer of 5. Okay, so the slope m, which again we denote it like this, equals 5. Okay, as expected. Okay, so now let's come back to the previous question. So what if we were interested in the slope of a tangent line at the point 1, comma 2, so when x was equal to 1. And the way that we know that from the definition is because we have a 1 here. Now, what if I wanted to know now when x is equal to 2, or when x equals negative 3, or when x is equal to 0? So that means that instead of a 1 in this formula, so right here, you have to put whatever number I give you. So in other words, you will need to redo all of this computation all over again with whatever points I provide to you. Instead of doing that, we would like to have a formula, a function, and once that when you plug in the number that you're given, the output is already the slope of a tangent line that you are interested. Okay, and we can do that very easily. Instead of having a 1 in this definition, we just put an x and then compute the expression of the slope in terms of x. That's going to give you a function which, as you may know already, it will have a name. It's called the derivative of f. Now, it's not just a particular point, it's just the derivative. So it's another function that when you evaluate at a point, the value that it will give you is this slope that we're looking for, the slope of a tangent line. Okay? So in other words, the derivative of a function is another function whose outputs are going to be the slope of a tangent lines. Okay? And the way we're going to define it is exactly the way that we define the slope of a tangent line, but instead of a, we're going to put an x in that formula. In other words, right here. You see this difference quotient? You just take the limit of the difference quotient as h approaches 0, and that's going to give us what we call the derivative of the function. That when you evaluate it at a point A, the output, the number that you obtain, will be the slope at that point. Okay? All right. So let me define that. So definition, this is the definition of derivative. Derivative. And let me say, so the derivative of f at x, or with respect of x, sometimes we say, or with respect of x, is the following. So the notation that we're going to use is, typically we're going to use this prime notation. So we put f or whatever the function is, and then we do a prime. Okay, f prime of x, and this is just the limit as h approaches 0 of the difference quotient. So f of x plus h minus f of x over h. So then, of course, once you compute this limit, okay, if it exists, of course. So let me say here, this is the derivative provided that the limit exists. So if this limit exists, this would be a function, and this would be a function of x. Okay. So for all x for which this limit exists, for all x for which this limit exists, and f prime is a function of x. It's a function of x, and its values are the slope. In other words, the range of this function, and is the slope of all possible tangent lines. The slope of the tangent line at the specified input, or at the given input. That's the reason why we call the slope m, we call it f prime, evaluated at the whatever value you're given, 2, 3, 1, whatever, because that's just the evaluation of this derivative function. Okay. So notation, we write derivative, we write in different ways. So we will be most commonly using the prime notation, but let me show you other ways that this can be written. So first one is called the prime notation. Then we also like to write this. Remember, y equals f of x. Okay. So mm, here y equals f of x. So this is called the Leibniz notation. So we write dy dx. That's another way of taking the derivative, d for derivative. And so this term d dx, we can think of it as being an operator. So you can write it like this as well. So what that means is we're taking the derivative of the function f. Okay, and d dx is like a package, is an operator. This is called the Leibniz notation. You will see why is this helpful when we talk about higher order derivatives later on. Okay, but for now we're going to be mostly using the prime notation, but keep in mind that the Leibniz notation is used from time to time. So let's see, as an example, let's find the derivative of the function above, x squared plus 1. So find the derivative of f of x equals x squared plus 1. So in this case, we want to find f prime of x. And remember, we have our definition. That's the limit as h approaches 0 of f of x plus h minus f of x over h. So let's compute this. So the point is that we do this computation one time, and then after that, we just plug in to get whatever slopes we want. Okay, so this is f of x plus h. Let me put it like this so you can see, and minus f of x. So f of x is just x squared plus 1 and divided by h. So this piece right here is our f of x plus h, and this one here is our f of x part. Okay, now let's simplify. So this is the limit as h approaches 0 of, in the first parenthesis, I'm gonna expand that square, 2xh plus h squared and plus 1, then distribute the negative, minus x squared minus 1 over h. So the x squares are gone, the 1s are gone. We still have 0 over 0, but notice that now whatever remains in the top, everything has an h, so we can factor it out. So let me do that. So we take out an h, so we get 2x plus h over h. The h cancel out, and when we take the limit as h approaches 0, we obtain 2x. Okay? So the derivative of the function x squared plus 1 is the function 2x. And then notice that if you want to find the slope of the point 1, 2, in other words, if you want to find the value of the derivative of 1, of course, that's equal to 2, as we saw in our computation above, right? The point is that we did the same limit, but instead of a 1, we put an x. But after that computation, now you can find all the slopes that you want. If you want to know now what's the slope, for example, at 0, what happens when x is equal to 0? Well, the slope is equal to 0, okay? And it makes sense. Let's take a look at the picture. At the point, let me actually write it here. So also at x equals 0, we have the derivative is equal to 0. And what is this? Remember, this is the slope. It's telling us that m is 0 at that point. And what does it mean for a line to have slope 0? That means that the tangent line is what? What type of line is it? Tangent line is a horizontal line. Those are lines that have slope 0, right? Because they're not going up or down. They are horizontal. So this is our function, y equals x squared plus 1. And then when x is equal to 0, we're talking about this point right here. And as you can see, that's the point at which the function has a horizontal tangent line. So here the slope is 0. Okay? So just keep that in mind. So that's the equation of the line itself is y equals 1, right? This equation is the line y equals 1, but the slope is 0. So we're going to be looking, these points are going to be special for us, okay? You're going to see that later on. So the moral of the story here is that if you have a function and you want to figure out where are the horizontal tangent lines, an equivalent question is when is the derivative equal to 0, right? Any point at which the derivative equals 0, this is telling us that we're going to have a horizontal tangent line, or we could have a horizontal tangent line. Well, actually, we have a horizontal tangent line because it's a slope. So derivative equal to 0 means you have a horizontal tangent line. Okay? All right. So now that we know this, let's do a couple more examples of other functions of finding the derivative. And then on Monday, we're going to continue on this, and then we're going to see, uh, you're going to learn the relationship between between derivative and continuity. So whenever a function has derivative at a point, we say it's differentiable at that point. Okay? And then a natural question is there a relationship between differentiability and continuity? Okay, so we're going to explore these and other questions on Monday. All right, so for now, let's get more practice finding derivative. And remember, the reason why we're interested in derivative is so that you can find equation of tangent lines. Okay, but we already did an example of finding equation of tangent lines, so let's focus now on the main ingredient, which is the computation of derivative. So find the derivative, and I want to do it for different type of functions. So we already did it for x squared plus 1. So now let's do it for a cubic function. Okay, let's do it for a rational function. Let's look at the simplest one, 1 plus x, just to illustrate the idea. And then let's also do it for the function square root of x. Okay, all right, so solution. So we have the function f of x equals x cubed plus 2x, and our job is to find the derivative. So f prime of x, remember, what we need to do is we need to compute the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x over h. Okay, let's do this. So sometimes this will be like a tedious computation, but as a price that we need to pay now, then later, of course, we're gonna spend a lot of effort in actually figuring out or finding rules or ways of computing derivative that do not really require the calculation of this limit. In other words, we'd like to get some formulas that will allow us to compute derivatives like this one very quickly instead of having to compute this limit all the time. Okay, but let's first suffer a little bit by just going through the definition and understanding what's going on, and then we will be in a position to be able to derive and use some other formulas, and that's what we're going to spend our effort the rest of the chapter, finding formulas for the different type of functions that you may encounter. Okay, but again, the limit definition is important because if you're given a piecewise function at that point at which the function changes formula, since you don't know what formula to use, then we need to look at a limit so we can specify a psi and then pick a formula. Okay, so that's why the limit notion is important. You need to know it. Okay, so x plus h cubed, so that is x cubed plus 3x squared h plus 3x h squared plus h cubed. That's how you span binomial cube. Then plus 2x plus 2h minus x cubed minus 2x. All of these divided by h. So let's see, x cubed here cancels. This 2x over here cancel with this one. And notice that in whatever is left, everybody has an h. Okay, so that's good news. We can factor out that h from what is left in the top, and then we get 3x squared plus 3xh plus h squared plus 2 all over h. The h cancel out, and then when we take the limit, anything that has an h is gone because h approaches 0, and we are left with 3x squared plus 2. So the derivative of the function f is 3x squared plus 2. Okay? All right. So, and every time that you have a polynomial, this is what you do. But the tedious part is, expanding the power that you're giving that shows up in the polynomial. It will be a little bit long. So, we would like to find some rules to do this very easily. And as it turns out, it's actually pretty easy to find this derivative once you know the rule, which we will talk about next time. All right, but for now, we're using the definition. So let's look at the other function, 1 over x. Again, we want to find the derivative. This would be the limit as h approaches 0 of f of x plus h minus f of x over h. So f of x plus h, that's 1 over x plus h. F of x is 1 over x over h. Again, this is a 0 over 0 situation. And as you know, in this case, what we should do is clear denominators. So I'm going to multiply top and bottom by the LCD. So everything in the top. So here the LCD is x times x plus h. So I'm going to multiply top and bottom by x times x plus h. Okay? To clear denominators. So for the first term, the x plus h cancel, and we just get x. For the second term in the top, the x cancel, and we get x plus h. And then in the bottom, nothing cancels, so we just keep the product as it is. So now we get limit as h approaches 0 of x minus h, or hx times x plus h. The x cancel out, so we get limit as h approaches 0 of negative h on top, and then h times x plus h. And this is good because the h cancels, and then we are left with limit as h approaches 0 of negative 1 over x times x plus h. And when you take this limit as h approaches 0, we obtain negative 1 over x squared. So, moral of the story, the derivative of the function 1 over x is negative 1 over x squared. You see, linear notation sometimes is useful because you may wonder, oh, but what is f? Well, you can write the derivative of 1 over x is negative 1 over x squared. And over here, in this example, you can write that the derivative of the function x cubed plus 2x is 3x squared plus 2. Okay? All right. And then let's look at the last one. The last one is an example with a square root. Our function f is square root of x. So you know what's the technique? In this case, we need to multiply by the conjugate, right? So let's see it. So f prime is the limit as h approaches 0, f of x plus h minus f of x over h. That's limit as h approaches 0 of the square root of x plus h minus square root of x over h. Again, 0 over 0. And the idea here is, as you know, multiply top and bottom by the conjugate, which in this case is the square root of x plus h plus square root of x. And we do that to get rid of the radicals on top. So difference of squares in the top. So we're going to get x plus h minus x, the first term square, kills the radical, minus the second term squared kills the radical, over h times the square root of x plus h plus square root of x. X is cancelled. And then we get h on top, and then this product in the bottom. This is nice. H cancel out. So we end up with the limit as h approaches 0 of 1 over the square root of x plus h plus square root of x. And we take this limit as h approaches 0, we get square root of x plus square root of x in the bottom, which is 1 over 2 square root of x. So f prime is 1 over 2 square root of x. And to write it in Leibniz notation, the derivative with respect of x, that's how we read it. d dx is derivative with respect of x of the square root function is 1 over 2 times square root of x. Okay? So again, so next time we're gonna do on Monday, we're gonna do a couple more examples. We're gonna find tangent lines, equation of tangent lines, so that you get more used to it. I already did one example like that above. We're gonna compute more derivative, and the idea is that we wanna move into, okay, let's try to see if we can calculate derivative without having to rely on this definition, without having to use the limit definition all the time, because it's long and tedious, okay? And you will see that depending on the function, there are formulas that you can use, okay? And that's how we're going to invest our effort from now on in the remaining of the chapter. Okay, guys, so with this, you can now answer most of the questions from homework 1, actually all of them. Not homework 1, but the first homework from the chapter, that would be, so what number is this? Homework 6, title instantaneous rate of change, derivative and tangent lines, okay? So I just wanna say one thing. So remark, if f of x is a position function, if this is a, let me call it f of t, because typically, you know, when we talk about a particle moving, our variable is time, our input variable is time. So if f of t is a position function, then first, the instantaneous velocity is v of t, and is actually the derivative of the position function. So, you know, it's the limit, and remember how we define this. This is the limit as h approaches 0 of f of t plus h minus f of t over h, okay? So that's what the velocity is. But then also, because there is a homework problem that you need to use this idea, acceleration. So the velocity is how fast a particle changes position. So it's instantaneous rate of change of the position function. But acceleration is how fast a particle changes velocity, okay? So it's the instantaneous, is the derivative of the velocity function. So velocity is derivative of the position function, and then the acceleration, is it 1c or 2c? No, 2c. So the acceleration, or instantaneous acceleration, okay, at time t is a of t, and then we define this as the derivative of the velocity function, okay? So if you want to find the acceleration of a particle, you first find the velocity. If you know the position function, find the velocity by taking the derivative of the position, and then you take derivative of the velocity to figure out the acceleration, okay? So keep that in mind, because this may show up in the homework, or it will show up in the homework. Okay, I'm gonna stop now.